Goswami from Kolkata, who will introduce us to the quantum isometry groups of the odd-dimensional quantum spheres.
Thank you very much. I am one of the organizers, but that is only honorary organizer. I think the real local organizer is Joydev and Rajada also and others. So I thank them for arranging this and giving all of us the opportunity to celebrate our beloved teachers and our Guru KBS Fest 75 years. Okay, so for some of the Indian participants, this will be probably a repetition because I gave not exactly same, but at 80% is similar to the talk I gave in few months back in IIT Bombay. So my apology to them, but for others, and particularly I think all people from abroad, this will be new thing. And as you can see, this is a joint talk with my current PhD student Shubhrajit, who is also here. So yeah, it's here. So you can discuss with him also. And I of course begin by wishing KBS a very happy and healthy 75th, which I did yesterday, but again I really like to keep repeating and take this occasion to express my respect, attitude for him. And with this, let me come to the topic of the talk. Well, so let me first briefly try to motivate or explain the basic philosophy of the quantum isometry and also quantum groups. So I am happy that already Uwe in day before this, in the first day I think, no, yesterday, right? Yesterday, yeah. So Uwe already introduced you to the framework of quantum groups, but I will again briefly repeat. So, and it's so this is a continuation, is a particular case study of in the framework of quantum isometry groups, which I am interested in and have been studying for last few years. And so it's a culmination of, I mean, not this particular talk, but this whole theory of quantum isometry. I must say that this is a joint talk of many of my students, ex-students, collaborators and others. I think I must have missed quite a few people, but try to name at least some of them. And these all began with this Suzhou Wang, Theodore Banica and Julia Pichon long back, mid 90s and 1000, but then I took it up much later in 2008 or so, and also with a slightly different geometric perspective. Again, so it's good to recall the definitions of compact quantum group. As Uwe already explained this, I don't really want to spend too much time on it, but keep the slide for some time. So for me this, yeah. So and this is the corresponding action, the definition of action, which should appropriately called a coaction from the algebraic point of view, but it's customary in Volanovich's theory to call it an action of the quantum group in analogy with the group acting on a space. So, we are viewing this as a non-quantum group, which is a generalizations of a compact group acting on a generalized non-commutative space. So, that is how it is viewed. So, I just give this slide, I do not explain because already Uwe explained these things, but let me keep the slides for some time. And right now, let me give some time on the next part of it, the other side of it, namely the non-commutative geometry. So, the realm of geometry according to Kuhn is this one. Of course, Uwe's talk, he took a different perspective, but from quantum group picture to build a non-commutative or approach it from there. So, I think this was probably not discussed so much. So, let me give some time on it. So, according to this definition, the geometry is generalized, or the generalized framework of geometry is given by such a data of a triplet. The very basic, at the very basic level is a triplet. You can add further structure to it as and when needed, but this is the common minimum, which consists of a subalgebra of a separate star subalgebra of a separable B of H of a separable Hilbert space, This subalgebra, of course, you do not expect to be norm closed unless for really trivial cases, because this is the prototype of the smooth function, if you like. So, this should not be norm closed usually, and the main thing is that the first order condition, the operator, this is the unbounded self adjoint operator and then subalgebra, and they are related by demanding that the commutator D commutator A for all A in this subalgebra admit bounded extension. So, this morally means that the operator the D acts as a first order operator, whereas the algebra is being thought of as a 0 order or functions. And if there is no further structure, you call it an odd structure, odd spectral triple, and if there is a grading which is compatible with the data, then you call it an even spectral triple, and the operator which is analogy from the classical spin geometry, call it the Dirac operator, the corresponding spectral triple. And then you often need some summability for doing any meaningful analysis on it, and the summability usually expressed with some summability of the corresponding analog of heat semigroup d to the power minus t d square. You can have also some finer or stronger summability, but we do not really need. So, I just mentioned the basic minimum summability which usually people require. And now, when one wants to generalize the concept of isometry from classical to non-commutative geometry. So, let me mention that just before I come to here, let me mention that this Gelfand type version, if you like, or rather the classical prototype example of this thing is come when you look at the L2 space of like a Riemannian spin geometry, a compact Riemannian spin manifold, look at the L2 section of spinors, and on that you have the classical Dirac operator. That will be really prototype examples of classical geometry this. Also, if you do not like to introduce or to have your this spin structure and so on, then at a more basic level you can also consider any Riemannian manifold, any compact Riemannian manifold. Look at the space L2 space of all forms, all differential forms with L2 space, and then you have your Hodge differential D, and this will be also another prototype example like. So, you can take your say A many compact Riemannian manifold, you take your Hilbert space as is L2 of all order of forms. So, you take 1, 2 up to 0 to dimension of M the forms, but you take the L2 closure using the Riemannian structure. You have a you can integrate forms like this, if it is a Riemannian structure G omega eta or omega whatever, or you can like this star omega wedge eta, and then you integrate with respect to that in form with respect to the volume measure of the. So, this L2 space you have a natural closed operator D plus G star, appropriate self adjoint extension of this. G is the usual Hodge usual D-round differential, and then this is also an example of take A to be C infinity M acting by multiplication on this section. This will be also a natural example of classical example of such spectral triple. So, which does not require the spin structure anyway. So, now coming back to it, suppose we want to generalize the concept of isometry to the realm of non-commutative space and non-commutative quantum groups and so on. So, for that the first one should look at how to characterize the classical isometry in some operator theoretic way, and for that you make this observation. Well, you can understand the group of Riemannian isometries of a compact Riemannian manifold as some universal object in the category of all compact metrizable groups which acts on M in a smooth and isometric way. And furthermore, smooth and isometric action can be understood if you dualize the action, if action is a point action. So, you consider the induced automorphism on the function level, infinition level, then the isometric condition is actually equivalent to that simple fact, operator theoretic fact, that it must commute with the Laplacian distance D. So, that brings me to the natural definition, which even which you can state and which you can explore, which you have done even beyond the classical geometry, that just call any action of phi on the groups. So, action of a quantum group, you call it an isometric action if it commutes with the corresponding Laplacian, and fortunately there is an analog of Laplacian in most of the non-commutative cases, and this can be built almost following the classical line of construction of this G and the D star D, which more precisely stated like this. So, under some reasonable regularity condition, which is this compact time and theta sum I will mention earlier, and which are valid in almost all the examples that you have, like the examples on the Riefeld deformed spectral triples and so on, you almost always get this regularity condition. So, these are fairly general. So, under such general conditions you can have actually analog of Hilbert's of forms. You have this analog of this differential map and you can prove its closability, you can construct this D plus D star and so on and so forth. So, only thing is that not always the Hilbert's of form will I mean maybe they are not finitely, they may not terminate. Sometimes it may have that, well, you have all n plus 1 going on even if manifold has a finite, sometimes that can happen, but not in deformed example. But anyway, but that does not deter you to define the Hilbert space of forms, and for this you actually need only 0 and 1 form, but you can construct all order of forms. So, in this generalized Hilbert space of 0 and 1 forms, you can define this analog of exactly this operator, and then you look at, and then usually for the theory, the next existence result we need also some further structure, which are all valid in all classical examples, and also they are Riefeld deformed versions, namely the L should have a compact resolvent and its eigenvector should be smooth in quote and some connectedness kind thing. So, these are some technical assumptions, but can be verified and are valid in most of the examples, many of the examples. And then you call an action of a compact. So, CQG is my abbreviation of compact quantum group. So, you call an action of a compact quantum group on the underlying sister algebra of this spectral triple to be isometric, so the isometric if it commutes with that Laplacian, or to be more precise, if you look at the slices of this action, then all of them should map this canonical algebra infinity to itself, and there it commutes with the Laplacian. And then in our first talk in this direction, actually proved that in this category there exists a universal object. So, it naturally is called the quantum isometric group of the associated spectral triple or Laplacian, and you can then of course you can relax some of the assumption and can generalize, that is a different story. But so this gave us actually a nice existence uniqueness theorem of some canonical compact quantum group associated to a spectral triple, which is analog of the Riemannian isometric group. But then we also wanted to associate something which is the analog of the orientation preserving isometric group, and also from another, looking at another point of view, it will be more natural because something which uses only the basic data D, not the other finer structure of Hilbert space of forms. So, for that we consider another similar category, and motivated by or rather guided by this classical observation. Okay. So, how do you characterize the orientation preserving isometry, the group of orientation preserving isometry on Riemannian spin manifold among the all isometries? Simple, it is just those which leads to a unitary representation of a 2 covering group on the L2 space of spinors, and there it commutes with the Dirac operator. So, in other words, the commutant of the Dirac operator will actually give you the, I mean the part of the isometric group which commutes with the Dirac operator after lifted suitably will give you the orientation preserving isometric group. And we did the similar thing, we tried to formulate and prove existence, uniqueness, etc. for a similar thing for a spectral triple. So, there we do not need the Hilbert space of forms or Laplacian anything, see only operator D is enough. And so, formally we consider this category. So, representation again Peter-Weyl theory representation, Hardstate was discussed or mentioned again in Uwe's talk. Here you can again just look at the definition. They are the direct generalizations of usual unitary representations of compact groups on Hilbert spaces. And so, here is the definition. So, we consider a category of compact quantum groups which admits unitary representation. Instead of actions, here we consider the actions, if you like, implemented by unitary representation. So, those who have a unitary representation in the Hilbert space of the spectral triple, where it commutes with the Dirac operator in this sense, I mean this U commutes with D tensor and DQ more precisely, and the associated action in quote implemented by this unitary, the add U, which will be a fundamental algebraic action, if you like, on this fundamental closure of Q, it leaves invariant this weak closure of the underlying spectral triple. So, that is the category we consider, and if objects will be for the obvious reason comparing to the classical situation, we call it the orientation preserving quantum isometries, and we did have some existence uniqueness theorem, but not generically. Usually we have to fix, we have to add conditions so that it preserves some canonical state or canonical volume, which in general kind of volume form, etc. However, for this particular class of example that I am going to discuss, it is important that sometimes, as I say, that sometimes there are some sufficient conditions. Look at this paragraph here. This category Q prime of quantum orientation preserving isometry in general may fail to have a universal object, but sometimes you can have, and one such important sufficient condition is involves actually the existence of a cyclic separating eigenvector of D, and which is valid in the class of example of quantum sphere that I am going to primarily going to discuss in these slides. So, but however, just let me just remark as a digression perhaps that well, in general, to have an universal object you have to restrict yourself to the subcategories of this orientation preserving isometry which also preserves some given state, then you have a universal object. For each such given state you can have a universal object and so on. But here somehow under the cyclic separating vector the corresponding state given by the cyclic separating vector will be preserved. So, that will take care of the existence. This part is slightly technical. I would like to actually just there are two things. Let me just say roughly. Okay, so here you have the universal object. It has its matrix coefficient of the unitary representation, but then you look at the corresponding add the implemented by that U, and the actually you pick up the subalgebra generated by those matrix coefficient, that will be usually in general a smaller sister subalgebra. So, you that is what is the relevant one. So, that is denoted by this Q iso plus D. And just remark that well, under some mild condition actually CG this corresponding earlier Q iso L, which I mentioned earlier in the beginning, something based on the Laplacian, will actually coincide with the some kind of orientation preserving quantum isometry for this operator D plus D star. And if you compare it with this classical thing, here you have this D plus D star, but its quantum isometry group of orientation preserving or that universal one which have a unitary representation commuting with this D plus D star is precisely actually usual isometry group. So, even the isometry groups can be viewed as an orientation preserving isometry group if you change your spectral triple. So, in that sense it is a more general perspective. Now, rest of the talk let me come back to examples. So, how much time do I have? 20 minutes, that is good enough. Thank you. So, now let us see some after examples of these concrete examples and different kind of spheres. So, as I said that the title of the talk was concerned with the quantum sphere. So, let me now come to the what are the quantum versions of spheres that I consider. And so, one of the most studied and most famous quantum version of sphere is the one which Fordovich Poodles and the earliest examples of in this theory of Fordovich's theory came the Poodle sphere, so called sphere Poodles, which is given by the 2 parameter and it is as a sister algebra given by these relations. So, you just observe that some of the if you look at this parameter value, particularly the mu, if mu becomes 1, this becomes a commutative algebra. Mu becomes 1, I think C0, something like C0 I think, C0 and mu 1, that will give you the exactly the algebra of the classical S2, function algebra on classical S2. And in general, so this SU mu 2 was already discussed in the talk, and this is one of the earliest and most studied compact quantum group in the Horonovich theory, and its representation theory, almost everything is known about it, many things known about it. So, its representation theory is very much like the theory of SU2, at least the leveling of the irreducible representations and its dimensions are exactly the same. So, this EL with L are the half integer, you can recognize these are the leveling of the irreducibles of SU2, and exactly there is a corresponding irreducible representation with actually the same dimensions, 12 plus 1 dimension for SU mu 2 as well. Only the matrix coefficient are becoming non-commutative now, and that is the difference you will have. So, you have a corresponding Hilbert space of L2 space of the GNS space of the Hart state, and there you have this EL M with EL, the Lth irreducible which is dimension 12 plus 1 occurring in the L2 of that Hart state in the 12 plus 1 multiplicity that the general federal theory gives you. So, in that you can identify this Poodle's algebra as the sister subalgebra which actually lives in a particular subspace, and then you constructed this it goes to the Arup and Partho who constructed such type of spectral triples on SUQ2, and you can restrict it to this Poodle sphere. This is one of the very first example on this Drinfeld type Q deformed spectral quantum group to have some meaningful non-trivial spectral triples. So, this class of spectral triple actually, except for this R, this D, that part is attributed to Arupta and Partho Chakraborty. So, to consider such this class of spectral triple, but not restricted to the sphere, the subalgebra, not the whole of SMU2, but the subalgebra. And then also we have some kind of another operator which actually related to the modularity of the Hart state, and this gives a functional or a state on this algebra, and we look at the quantum isometry group, the universal quantum group which have a representation commute with this D as well as it preserves this R denotes, it preserves the functional associated with this operator R. We just I recall once more here. So, this Q iso R plus D is nothing but the universal compact quantum group which have a unitary representation on this Hilbert space H which commutes with D, and as well as it also preserves this functional given by trace Rx. That was the definition, and such things once you fix such functionals in addition to the requirement of commuting with D always exists, universal object always exists, and here in one of our paper with Jyotishman we actually computed and identified this corresponding universal quantum group. So, which should be thought of as a orientation preserving quantum isometry group for this particular non-commutative geometry on the Poodle sphere with the mu twisted version of SO3 as expected, which you can think of a in the natural analog of the fact that classical 2 sphere has this isometry group SO3, actually O3, but here we have some kind of there is a slight catch here which I will not go into that, but here this orientation preserving kind thing lead to SO here actually. Now, the other type of sphere which again was discussed, or at least the orthogonal group corresponding orthogonal groups was discussed at length with Ove's talk. Again, it is good to recall that you have the various versions of free, half liberated and liberated versions of the orthogonal group ON and the corresponding spheres. So, these are the first one is of course, you have no relation except for the summation xi square 1 and they are self adjoint, and exactly the similar thing in corresponding ON. And you can have the half liberated version where you have added the extra commutation relation, where something with the 3 things xi jk in between keeping one j, then xi and xk will can be swapped, that is the half liberated thing. It is not fully free, neither not fully commutative, but is a mixture of a kind of that. And then of course, you have the other half various things. So, corresponding orthogonal group, and as we have already pointed out, I think in our briefly mentioned about this work with Manika, where we have identified, we have written down some natural sectoral triple Gaussian state, and then identified these corresponding orthogonal group, quantum orthogonal groups, as the natural quantum isometric groups of those corresponding quantum spheres. This is another examples of where we have computed the isometry of spheres. Now, here is a more recent result with Subrajit, where we looked at the analog of these things, but for odd dimensional quantum spheres, or we can think of this as a complex spheres, the same thing. Viewed as a real sphere, deformation of real sphere, you should do an odd dimension, or you can just think of them complex sphere. So, they are classically these are what? These are nothing but the complex n minus dimension sphere given by this, and the corresponding universal group, either you look at it in a natural geometric point of view, or just look at the what is the universal group that acts linearly, meaning which preserves this canonical set of generators, the span of the generators, then you easily see that you really get nothing but the corresponding unitary group UN. So, UN will be the universal group for the classical complex one sphere, which on which it acting linearly, and you can also identify it as a natural isometric group if you want to put a natural invariant structure on the sphere and so on. So, we want to basically generalize this result to the quantum realm, and for that look at, we recall the definition. This is not due to us, this is already quite old, people studied it, well studied examples of sister algebra. So, it is the quantum sphere, it is a unital algebra generated by these generators Zi and Zi star, which have, as you can see, there are various relations. If you put q equal to 1, you get back the relations of usual sphere, because then Zi will be commute, they will be normal and they will be commute, normality comes from here, commuting coming from here, and then this becomes then same as Zi bar or Zi bar Zi 1. So, this will become exactly the, and this relation simply will be again a normality relation. So, you put q equal to 1, you get back the relation of complex n minus 1 sphere, and this is a twisted non-commutative sister algebra out of that, twisting those relations. So, that is why it is naturally called a quantum sphere, and it has of course the natural star structure, and moreover, okay. So, then let me discuss a little bit of the corresponding quantum group version and a slightly algebraic point of view. So, there is the FRT bialgebra, Fadev, Eskin and Takkajan, I think I can pronounce this correctly. So, this FRT bialgebra is by definition is or also called the coordinate algebra of quantum matrix space, is a quantum version of the Mn, is a free unital algebra, complex algebra given by these n squared generators, which as you can see these are the matrix elements. So, they are non-commuting because of the appearance of q here, q there, but some of them are commuting. There are some relations which will give you commutation, but not all of them commute, and then also there is other relations. And just like the classical matrix algebra, Mn, this also has the natural matrix coproduct and also a co-unit. And furthermore, you can have an analog of a determinant, which order is not here, and maybe you do not compare with it, but Gadadhar's version was a free version of this thing, and this is of course a q twisted version, but this is also again a non-commutative determinant. Sorry, yeah. So, this is a determinant that this is now very almost like the usual determinant, except for of a matrix, except for you have appearance of, instead of minus 1 to the power L pi, you have minus q to the power L pi, otherwise it is similar. And then you can quotient this by the corresponding ideal generated by this element dq. So, formally you do this, you look at the a polynomial algebra with one indeterminate in MQN and this quotient by T dq1 where dq becomes invertible. So, we localize by dq putting it algebraically, and the corresponding algebra as we expect should be called the version of GLN and is called so. Just like the way you obtain from GLN from Mn, you can do the same thing in the quantum world and getting the GLQN or the corresponding coordinate algebra of that by this prescription, and this becomes a Hopf algebra and with the antipode given by this. So, given this, you can go further and look at a real structure, real or star structure on this Hopf algebra, simply by putting this, defining Uij star by this antipode applied on Uji, and that Hopf star algebra is actually corresponds to the so called quantum group UQN is yeah. So, with this star structure dq becomes actually a unitary element, and you have a canonical coaction of this UQN on the algebra of sphere which is in the before. The formula is basically same as the defining formula of usual UN on Sn S2n. So, then you can further go down to SUQN by demanding this dq should be 1. So, identifying dq is 1, you can quotient and define the algebra of SUQN, and similarly this also identify the coordinate algebra of the quantum sphere as a suitable subalgebra of co-ideal subalgebra of SUQN and so on, and then the restriction of the Hart state. So, this becomes a compact quantum group SUQN, and restriction of its Hart state to the subalgebra which is the completion of this OS2QN inside O of SUQN. If you restrict the Hart state of UQN onto the subalgebra, then that becomes a unique UQN invariant state of it, just like the usual integral, volume integral on the sphere, classical sphere is the unique UN invariant measured on that. So, then we present the main results, that means the algebraic results. I have two results, one is the algebraic version, called the algebraic quantum symmetry, the other is a more in the analytic framework. So, the first algebraic one. So, algebraically, take any Hofstadter algebra which have a coaction on this coordinate algebra of this odd quantum sphere, and also suppose the action is such that the coaction preserves the canonical generators. So, it leaves invariant the set of span of the generator Z1, Z2, Zn, and also it preserves the inner product on this span given by the restriction of Hart state on third function on this. Then you can prove that this is the universal one in this category is nothing but UQN. There is a unique star morphism of from OQN to this Q such that this coaction is compatible with the canonical, is a sort of it's the projection of the canonical coaction of UQN on this algebra. So, in other words, to put it simply, UQN is the universal CQG type Hopf algebra, complete quantum Hopf algebra, which have a coaction which is linear in this sense written there, and which preserves the Hart function. And then let me state the analytic version. How much time? 5 minutes? 7 minutes, good enough. So, I just want to state that. So, now to state the corresponding analytic result. So, in our in terms of the quantum asymmetry group introduced in the beginning of this talk, I have to just quickly recall or quickly describe the representation theory of SUQN, or in other words the representation theory of SUN. I mean, they are exactly same as far as the labeling is concerned. Of course, the matrix coefficient are non-commutative just like SUQ2. So, in the more general case it is also true, that is true for in fact any Dirichlet-Jimbo quantization. So, just like you label the irreducible representation by the Young tableau, I mean this just reminds me, I happily remember that this thing Young tableau and this theory was first introduced to me by KRP in his course, this harmonic analysis course. KRP, do you remember? You can't hear. You introduced us to the in your harmonic analysis course to the Young tableau. So, I thank you again for when I given this talk, with happy memories. So these are given by these Young tableaus or labeled by these non-negative integers in a decreasing order, and let H lambda be corresponding finite dimensional Hilbert space on which this irreducible acts. And then one can show that, well, when you look at to the subspace, look at the subspace of the sphere inside this SUQN, then not all irreducibles are there, only a class of irreducibles occur there, namely those given by this n plus k comma k dot 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 k 0, this type, which are denoted by lambda n k. So, with multiplicity 1. So, that is the description of the L2 space of the odd quantum sphere inside this GNS of SUQN. And there also you can have a, again following Partho and Arubda and Partho's work, we have a spectral table there, they have constructed a spectral table there, which is given by such things. So, this is one example of a spectral table there, where we have our Dirac operator is a diagonal operator with respect to on these irreducibles. So, that this Dirac operator naturally UQ equivariant Dirac operator, it commutes with the corresponding UQ in action, hence it must be acting by scalars on each of these irreducible pieces, and the scalars you can choose suitably. One choice is g n k is minus k if n equal to 0 and n plus k if n positive, then you can prove that this will be a spectral triple. And this is a compact type, and this has the property of cyclic separating vector, namely the vector 1 of algebra is given as a cyclic separating vector, which is also an eigenvector. So, here we do not have to specify a state and the q iso exists, and we can actually identify this corresponding q iso plus as again by UQN. And I do not go into the proof, I do not have time and do not want to, slightly not difficult, but it uses a little bit of representation theory, some induction argument, combinatorial argument is needed to prove this fact. Basically, one way is clear that basically to prove that is something, any action, anything commutative with D can be linearized, and conversely any linear action actually can be extended on the whole. So, it must preserve each of the eigenspace. So, that requires a bit of combinatorics, and that was mainly our work, but I just stop with the statement and the open question. So, it is a natural open question, can I generalize this for an even dimensional quantum spheres, and that is not yet known. And for example, you just saw a similar version with this S2, which is my joint work with Jyotishman, but that does not really follow from this general theorem, because this considers only the odd dimensional quantum spheres, and the other S2q for the corresponding Poodle sphere was sort of done by hand. So, we do not yet know, and there are some conceptual problem related to the multiplicity of the eigenvalues of the so called Hecke operator. We just consider this much. In these odd cases, the Hecke operator has only 2 eigenvalues, but in some even cases it will have 3 eigenvalues, and so then that creates a problem for our strategy what to work there. So, we are still thinking, and also I will be happy to know if we can generalize this result maybe by slightly some adapting the technique little bit to cover also the even spheres. But so far we have not done except for the S2 case, but that is by a completely different computation. That is why. Okay, so I stop here. Thank you.
Thank you very much for your talk. Are there some questions or remarks? Son?
The existence of a cyclic and separating vector, does it essentially produce a state which
okay,
volume form or something?
GNS state will be preserved,
yeah,
so
that creates the maximum. Okay, yeah. And the other small question is that so I had not noticed this previously when you had given this talk, but the Riemannian, the category where it resides, the classical object, is metrizable. So how do we generalize metrizability to the?
Say it again.
No, when you wrote the definition that the classical group, the classical Riemann, it is metrizable in the category of compact metrizable. So
compact topological, well, I mean, you don't have to generalize really. Here, this thing, the way it has been said, so I can also say that just compact Lie group or some compact group. So that part I think comes for free, so to say.
I see.
So really, you don't have to.
So you don't have to care about that.
Don't have to care.
I see.
I mean, universal group, compact group will automatically becomes the Lie group and will be metrizable. So you can also state the category universal compact topological group. The metric, I wrote it somehow, and you did not need really. You can just drop that word. Any compact group is just a word.
Further questions? If not, then it's time for coffee. So let's
Yeah.
thank all speakers again.